You see them every time you cross railroad tracks. Millions of them. Gray, jagged, rough stones stretching for thousands of miles. They're beneath every train in the world. India, Japan, America, Europe. The same stones. Always the same. But here's what's strange. Nobody knows why they're there. You've probably never thought to ask. Most people haven't. But when you do ask, when you actually stop and wonder why we rest our most advanced trains on a pile of loose rocks instead of solid concrete, the answer reveals something brilliant. Something that connects ancient sailing ships to modern railways in the most unexpected way. Think about the weight. A loaded freight train weighs 12 million pounds. That's equivalent to 6,000 cars stacked on top of each other. If you place that weight directly on the ground, something catastrophic happens. The pressure is so intense it crushes the soil beneath it. The earth compacts. Muddy water oozes up. The track sinks into the ground like a foot sinking into wet sand. Once the track sinks, it warps. The rails bend. They twist in opposite directions. And when rails twist, trains derail. People inside can be seriously hurt. So engineers faced an impossible problem. How do you support millions of pounds without the ground collapsing underneath? The solution is surprisingly simple. Imagine a layer cake. On top, you have the steel rails. Below that sits wooden or concrete beams called sleepers or ties. And underneath, everything sits the ballast, the stones. This three-layer system does something remarkable. It takes that crushing pressure and spreads it out. Instead of all 12 million pounds pressing down on one point, it distributes that weight across a huge area. It's like the difference between wearing high heels and wearing snowshoes. High heels concentrate pressure. You sink. Snowshoes spread weight. You float on top. The stones act the same way. They cushion the impact. They absorb vibration. They let the track breathe instead of breaking. But here's what makes this system actually work. The stones aren't smooth. If you pick up a piece of railroad ballast, it hurts your hand. These stones are sharp, angular, ugly. They look like they've been smashed by a hammer. And that's exactly what happened. Engineers crushed granite and quartzite into jagged chunks. Why? Because smooth stones would be a disaster. Imagine stepping into a pit of ball bearings. You'd slide everywhere, right? Smooth stones roll. If a train rumbled over smooth, round rocks, the vibration would make those stones roll sideways. The track would slide apart. The whole system fails. But jagged stones interlock. Their sharp edges grip each other. They lock together so tightly that even 12 million pounds of weight can't shift them. The stones become like a solid mass. Yet somehow, they still flex slightly. They still absorb shock. Angularity is everything. But weight and friction aren't the only problems ballast solves. Water is the silent killer of railways. Heavy rain falls on a concrete slab track. It pulls up. It sits there. Steel rusts. Concrete cracks. But ballast is porous. Water flows through instantly, like a giant French drain. The ground stays dry. Solid. The track doesn't weaken. And then there are weeds. You rarely see a jungle growing through the middle of a train track. That's not by accident. The thick layer of sharp rocks makes it nearly impossible for plants to take root. Seeds land on the stones. They can't penetrate. The roots can't push through the jagged surface. Plant roots would otherwise break up the soil and destroy the stable foundation. The stones prevent that. One material solves three problems: weight, water, and weeds. Now here's the part that blew people's minds when they discovered it. The name ballast comes from ships. For centuries, wooden ships sailed empty across oceans to pick up cargo. But empty ships are disasters. They bob wildly in waves. They're unstable. They sink easily. So sailors filled the ship's hold with heavy stones. This weight stabilized the vessel. It kept the ship upright. They called this weight ballast. When ships arrived at port, sailors dumped these stones on the shore. Mountains of discarded ship ballast accumulated at ports worldwide. Early railway engineers were desperate. Trains were new. They were expensive. They needed cheap, heavy material to stabilize their tracks. They looked at those massive piles of abandoned ship stones and realized, perfect. They took the maritime ballast and used it for trains. The name stuck. But this ancient solution is facing a modern challenge. Engineers realized they could build concrete slab tracks instead of ballast. No stones, just a solid concrete foundation beneath the rails. Seems better, right? Japan thought so. High-speed trains on the Shinkansen run on concrete slabs. Europe does the same with their 200 miles per hour rail lines. The concrete works perfectly for extreme speeds. But here's why we haven't switched everywhere. Cost. Concrete slab tracks cost 3 to 4 times more than ballast systems. To replace all American railway ballast with concrete would cost hundreds of billions of dollars. Railways can't afford that. So the ancient solution persists. It's cheap. It works. It's proven over 200 years. But ballast has a secret problem that's becoming impossible to ignore. Stones break down. Train vibrations are constant. Year after year, vibration fractures the stone. The weather cracks it. Frost expands it. Rain dissolves microscopic layers. The stones get smaller. They become powder. They settle. They are compact. Voids form between them. These gaps weaken the entire system. The ballast stops working properly. Pressure isn't distributed evenly anymore. The track becomes unstable. Railways have to replace the entire ballast layer every 20 to 30 years. That's millions of tons of stone removed and replaced annually. The environmental cost is staggering. Quarrying requires explosives. It destroys habitats. Transportation creates carbon emissions. Worn ballast contaminates soil with oil and fuel from train leaks. Disposal creates environmental hazards. Maintenance crews spend billions every year just keeping ballast functional. The system is reaching its limits. Climate change is making it worse. Extreme flooding saturates ballast. Permafrost thaw undermines tracks in Arctic regions. The ancient solution is cracking under modern pressures. But engineers just developed something that could revolutionize everything. They're embedding sensors directly into ballast layers. These sensors detect vibration changes instantly. They measure stress on the track. They monitor water infiltration. They send continuous data to artificial intelligence systems. The AI learns patterns. It predicts failures weeks or months before.